We're living in the era of the AI giant. If you look at the headlines, it's all about bigger. Billions of parameters, trillions of tokens, and data centers that consume as much electricity as small cities. But here's the problem. You can't fit a data center in your pocket. If we want AI that is actually useful, meaning it's fast, it's offline, and it doesn't cost a fortune to run, we have to make it smaller. But usually, when you make something smaller, it gets worse. A tricycle isn't as fast as a Ferrari. But what if you could distill the essence of that Ferrari into a smaller frame? What if a tiny model could inherit the wisdom of a giant? Today we're diving into the world of AI distillation. It's the secret sauce used by companies like OpenAI and Google to make models like ChatGPT Turbo and DistilBERT possible. We're going to look at the tech behind it, and then answer the controversial question of whether this is actually stealing intellectual property. And finally, explore how this technology is democratizing the future of intelligence. So, what actually is distillation? Formally, it's called knowledge distillation. Think of it as a mentor-apprentice relationship. In the AI world, we have two main characters, the teacher and the student. The teacher is that massive, complex model we talked about. It's been trained on a literal mountain of data and has incredible accuracy. But it's heavy. It's slow to respond and expensive to keep running. The student, on the other hand, is a much smaller, simpler neural network. If you just train the student on raw data from scratch, it would probably be pretty mediocre. But in distillation, we don't do that. Instead, we train the student to mimic the teacher. The goal isn't just for the student to get the right answer. It's for the student to understand how the teacher thinks. Now, why does this work? It's because large models often have overcapacity. They have billions of parameters, but they don't always use all of them effectively for every task. Distillation finds the most important patterns and packs them into the smaller model. The result? You often get a model that retains 80% to 97% of the giant's performance while being a fraction of the size. You might think this is brand new tech from the 2020s, but the roots actually go back to 2006. A researcher named Caruana and his team were working on a problem. They had built this ensemble model, essentially a huge group of hundreds of classifiers working together. It was incredibly accurate for the time, but it was a computational nightmare to actually use. Instead of giving up, they tried something radical. They used that massive ensemble to label a huge dataset, and then they trained a single, tiny neural network on those labels. The result? The small model matched the performance of the giant ensemble while being 1,000 times smaller and faster. That was the eureka moment. It proved that knowledge could be transferred. But for a long time, this tech stayed in the shadows. It wasn't until the recent deep learning revolution, where models got so big they started breaking budgets, that distillation became an industry standard. Okay, let's get a little under the hood. Don't worry, I'll keep it simple. If the student is mimicking the teacher, what exactly is it looking at? In normal AI training, we use something called hard labels. If the model says dog, it gets a point. If it says cat, it fails. It's binary. But distillation uses soft labels. Imagine that same picture of a golden retriever. A giant teacher model doesn't just see dog, it sees a probability distribution. It might say, 90% chance it's a dog, 9% chance it's a cat, maybe because of the fur texture, 1% chance it's a car. Those soft labels are pure gold for the student. They show the student the nuance. They show what the teacher was uncertain about and which classes are similar to each other. To get these soft labels, we look at Logits. These are the raw, unnormalized outputs of the neural network. They are rich with information about the model's reasoning process before they get squashed into a final yes-no answer. There are two main knobs we can turn here, temperature and alpha. Temperature, T, softens the probability distribution. A higher temperature makes the differences between classes less extreme, which helps the student learn the uncertainty of the teacher. Alpha is a balance scale. It tells the student, how much should you listen to the teacher's soft labels versus the actual ground truth data? By tweaking these, we can train a student that doesn't just memorize the right answers, but actually inherits the logic of the teacher. Now, we have to talk about the elephant in the room. If I use your billion-dollar model to train my cheap million-dollar model, am I stealing your hard work? This is a heated topic in the AI community, but we need to make a distinction between the technology and the intent. Technically, distillation is just a compression method. It's not inherently good or evil. When is it ethically gray or flat-out wrong? Unauthorized API use. If a company pays for access to a competitor's proprietary API and uses those outputs to build a clone model without permission, that's a major legal and ethical issue. Data rights. If the teacher was trained on stolen or copyrighted data, the student inherits that poisoned legacy. Reverse engineering, using distillation specifically to crack a competitor's secret sauce, is where IP lawyers start getting involved. But on the flip side, distillation is often used perfectly legitimately. Companies like OpenAI distill their own models to make them faster and cheaper for us to use. Researchers use it on open-source models to help make AI accessible to people who can't afford a $10,000 GPU. The ethical framework shouldn't be, is distillation bad? It should be, do you have the right to the teacher model's knowledge? So why is everyone obsessed with this? Why not just build better, big models? Because the benefits of shrinking them are massive. First, size and speed. A teacher might have 20 billion parameters. A student might have only 3 billion. That means it's not just smaller, it's dramatically faster. Think about a chatbot. If you have to wait 10 seconds for a response, the magic is gone. Distillation makes that response near instant. Second, it saves the planet and your wallet. Large models are energy hogs. Running a distilled model requires less power, fewer GPUs, and lower infrastructure costs. It makes AI sustainable. Third, task specialization. Sometimes you don't need a model that can write poetry, code in Python, and explain quantum physics. You just need a model that is really good at one thing. Distillation allows you to create specialized students that are faster and more accurate in a specific domain than the general-purpose giant. In short, distillation is how we make AI accessible, sustainable, and specialized for the real world. Now, I'd be lying if I said there was no free lunch. Distillation has some serious drawbacks you need to know about. First, the reasoning floor. When you compress a model, you lose depth. While a distilled model is great at pattern matching, it often struggles with complex, multi-step logical reasoning. It might give you the right answer, but it's a shallower understanding. Second, inheriting the sins of the father. This is a big one. Distillation propagates bias. If the teacher model is biased against a certain group, or if it hallucinates facts, the student will learn those exact same flaws. Distillation doesn't fix a bad model, it just makes it smaller. Finally, the capability ceiling. In almost every case, the student cannot exceed the teacher. It's a hard cap. If your teacher is mediocre, your student will be, at best, slightly less mediocre. So, where does this leave us? Is the future of AI just a series of smaller, flawed students? We are moving toward a world of agentic AI, tiny, specialized agents that live on your phone, your watch, or your medical devices. These won't be trillion-parameter giants. They will be highly efficient students, distilled from the best teachers on the planet. Knowledge distillation is the bridge between laboratory AI and real-world AI. It's how we take these incredible advancements and actually get them into the hands of people. Specifically, people who don't have a massive server farm in their basement. It's about accessibility. What do you think? Is distilling a model an act of engineering genius, or is it just a clever way to copy homework? Let me know in the comments below. I'm really curious to hear your take on this engineering trade-off. And if you want to dive deeper into the technical papers I mentioned today, I've linked them in the description. Don't forget to hit subscribe if you want more deep dives into the tech shaping our 2026 world. I'm your host, and I'll see you in the next one. Keep exploring the future of AI.